Indian mathematics kind of extremely famous in number theory, algebraic geometry, in many other areas, but no, maybe not so was in kind of geometry topology and symplectic geometry area. And so I hope this area now, and gradually, I already, since like first time I was here about 10 years ago, and I already see quite a lot of new people in this area, so I hope this will continue. So it's for me the kind of also, I'm not exactly sure what I'm going to do, and I should tell that like within last 3 days, I kind of every night I was just kind of rethinking what I was going to talk about, and so kind of like so I was changing 180-degree my plan, what I plan to talk, but kind of roughly we'll see. Okay. So also one more kind of general thing before I start, I want to say that this is a very small group, and please ask questions, right? So it's kind of don't be kind of hesitant. So if because I think so it's not too loud. So I hope like in a while I kind of adjust to you, I would understand better what you know or not, but at the beginning maybe not, and so kind of stop me if I pronounce something which kind of not clear. Okay? Okay, so let's no, it's too loud. Kind of like yeah. So let's start with just the following question, like which really motivates us all this discussion during this my lecture, short lecture course, is the following question. So we have a function of, like for instance, just on interval function of one variable, right? And like we like when you have a function, we like to draw graph of this function, right? But then of course, this is a, for instance, I write this x and I write z, and I have a z is some function of x, so this is a graph of this function. But then we can also maybe useful also to draw graph of derivative of this function, right? So here's the derivative positive, here's the negative. So okay, I'm not kind of drawing this accurately, but something like this. You get a function, and you get this curve in the you get two graph. But it would be convenient to draw. So let's call this y is equal f prime of x. And now I would like to have this coordinate x, coordinate y, coordinate z, and then I would like to simultaneously take it like curve in 3 space such that it's a one coordinate is graph of function f, another coordinate graph of function of its derivative. So you have a curve in 3 space which kind of simultaneous graph of function and its derivative. So now what a kind of curve is this, right? Okay, so of course you have this coordinate coordinate z. So what we can write is a kind of dz is equal f of x dx. Okay, so let's call this maybe g of x, this prime. So you have a dz is equal this g of x dx. Or just I can write dz is equal y dx. So what does it mean? What does it mean, this equation? So this equation, so this is a so-called differential one form, and this sometimes equations of this type are called Pfaffian equation for the German mathematician of 18th century named Pfaff. And so what this equation define, right? So you can just think what does dz dx means. So you have our 3 space, and you have a coordinate x, y, z. But coordinate x, y, z we can only apply to vector originated at origin, right? So you have a vector originated in origin, then it has a 3 coordinate x, y, z. But then I also would like to consider vectors which are originated at some other point. And so how I denote coordinates at this point? And the coordinate at this point is precisely dx, dy, and dz. So dx kind of like, what is dx? Dx is the differential of this yz. So it's kind of linear part of function. And so linear part of function x at the point like 1, that means that x minus 1. You just need to have a, because x, if your origin at 1, is not linear anymore. So you have to subtract 1. So you have this coordinates dx, dy, dz, kind of like, which is a copy of x, y, z, but kind of shifted everywhere. And then we have this, maybe I will denote this differential one form, dz minus y dx. This is a linear function for every point with coordinate x, y, z. This is a linear function on the space, and it defines a plane, right? Because linear equation define a plane. And what kind of plane is this? It's a plane because there is no dy. This is a plane which is always containing y-axis. So you can draw all y line parallel to y-axis, and you have what is called field of planes, which are tangent to y-axis, and slope of this plane in dz dx direction is changing, is equal to y. So what you get kind of field of plane, which kind of like, which is tilting and going along this line. And this is an example what is called non-integrable plane field. So non-integrable plane field, that means that this plane field is not tangent to any surfaces. So you cannot like foliate our 3 space by surfaces such that this plane field are tangent to it. You cannot, in fact, of what I'm going to do, it kind of immediately follow that such thing does not, you cannot find even locally, you cannot find in integral surfaces. And such plane field is called contact structure. So this is like our first encounter of symplectic geometric object. You'll see what it is. So that's how it is. So again, contact structure is what is called non-integrable plane field, and there is a many kind of definition of what precisely means non-integrability. One definition could be the following. So you have a plane field, so you have a space, and this is in this space you have a plane field. So that means at every point of the space you have a plane. And then what does that mean? It's non-integrable. That means that you can like choose a basis at every plane. And then you get 2 vector field, right? Like vector field v1 and vector field v2. And so vector field or line field you get, and vector field are always integrable, because this is a like basic fact of ordinary differential equation. It's called Picard theorem, that if something is smooth enough, it's always integrable. So therefore, you can always find trajectories, some curve, such that velocity vector is the cell vector field. And then you can just take any point, follow this vector field, and then take a second vector field, follow it, and then again, so say for time t, and then maybe for some small time t, and then again for another time t, follow here, and then for time t, follow back, and then come here. And the question, do we come to the same point or not? So we're not necessarily coming to this point, and there is some kind of displacement with respect to our original plane, and this displacement divided by t square and send t to 0, and then you get some vector which is transverse to our vector field. And if this vector field is vector not 0 at every point, that's what it means on integrability. So it's called Lie bracket of the 2 vector fields. So the Lie bracket of 2 vector field, if it's not 0, if it's not non-zero, but if it's not it has a component not in our vector field, then it's a non-integrability. So on this calculus of the irrational form, this just means that if you take a differential of alpha, kind of which is a differential 2 form, and then if you restrict this to our plane field, which say I denote this plane field by xc. So if you restrict to xc, so this is never 0 at any point. So that's non-integrability. So this is a kind of definition of context structure. And this is a, maybe I will not want to go, because this is a, I start very slow, but kind of still my goal to come to quite advanced stuff. So therefore, I have to kind of a little bit start to speed up in my lecture, but let me continue slow for a little bit more time. So this plane field kind of like, there is a this object kind of naturally arises in kind of in nature, kind of this type of object arise, and like basic example of this is a skating problem, right? So in mechanics you have some mechanical system, and this mechanical system determined by what is called configuration space. So there is the set of all position of this system called configuration space. For instance, you have a particle moving in the space, configuration space is our R3, particle moving on the plane, configuration space R2, and then could be some constraint. For instance, this particle required to move along some surface. And this constraint of this type is called holonomic constraint. But there are some other constraints, and like constraint like here, that this particle required to move all the time in direction to tangent, for instance, to this plane field. And where we have this thing, we have this in the problem of skating. So if you're skating on this like ice rink, then position of the skate is determined by 3 coordinates. You have a position, like it's a figure skating. So you think your skate touching at one point, kind of like this skate. And so you use the point of contact, and then there is also, you can, direction of the skate, there you have some angle. So you have a three coordinates. So the configuration space is a product of this R2, of this our plane, times the circle, which is this angle. So you have a 3 coordinates. And now what is our constraint? You constraint that if you take a velocity vector, and in mechanics, so the constraint is the following. So you're only allowed to skate in direction of the skate. You're allowed to rotate on one place, but you're not allowed to kind of to move perpendicular to skate, right? So that's not possible. And so that means that if you take a like velocity vector, so usually in mechanics velocity denoted by dot, so you have this x dot, y dot, and this should be proportional to this vector, so it will be proportional to vector cosine theta sine theta, right? And which means that determinant should be equal to 0, so that means that x dot sine theta minus y dot cosine theta should be equal to 0, right? So this is condition, and this is of course just means that if you what that means, that precisely means that our velocity vector is tangent to the plane field given by this Pfaffian equation sine theta dx minus cosine theta dy. So if you take this plane field, so our vector field should be in this vector field, the vector plane, so it will be tangent to this one. And this one, in fact, locally, it's the same thing as this one, because like you can say, if say cosine theta is not 0, you can divide and then just denote tangent theta by y, and then you get the same formula. Okay, so this is a kind of example of context structure. So I'm saying that context structure kind of naturalized kind of as a what is called mechanically non-holonomic constraint. So this is kind of Okay, so you can go to high dimensions. So for instance, you go to 2 dimensions. So you have a so you have a function with of 2 variable, and now you have a function of 2 variable, and I want to draw simultaneous graph of this function and its first 2 partial derivatives. So now I need 5 coordinates. I have coordinates x1, x2, y1, y2, z. This is a coordinate for, this is like placeholder for function. This is a for its first partial derivative. This is a for second partial derivative. And then you can also consider this contact structure. You get condition that you have a dz minus y1 dx1 minus y2 dx2 is equal to 0. And then condition of surface to be tangent to this plane field is precisely condition that this surface is a graph of simultaneous graph of function and derivative. So this, as I said in here, this is like in 1-dimensional case. This plane field is non-integrable, but it's kind of still a little bit integrable in the sense that still there are plenty of 1-dimensional integral curve, as we've seen, and such curve called Legendrian curve. So and here you have it's also non-integrable, so it's a 5-dimensional space. You have a 4-dimensional plane field. You cannot find this 4-dimensional integral surfaces. In fact, you can prove that you even cannot find 3-dimensional integral surfaces, but 2-dimensional integral surfaces exist in abundance. This is an example of them, and they are called Legendrian. So this is the Legendrian curve, and this one. So you can ask in opposite direction. So if you have this graphical surface, you have a x1, x2, and now in 5 space you have some surface S. And suppose the surface is Legendrian. So that means that suppose it's tangent to this plane field. The question is, can you find the graph, such graph, such function? And answer, yes, provided that the surface is graphical. So that means the surface projects to the base without singularities. Or in this 1-dimensional case, when you have this when you have this in 3 space, you have this curve, and if it so if it kind of graphical, when you project to xz plane is graphical, then automatically the second coordinate is just derivative of this function. But it could be some point where this our curve is in fact tangent to y direction, right? Because y direction tangent to contact structure, so our curve can go in one direction, and therefore when I project to this plane, it have a singularity, and what you can check the singularity is then it will generically look like what is called cusp point. So what we get when you project general Legendrian curve, you get picture like this, which is called which smooth curve with this cusp, maybe some self-intersection, and this picture is called front. So that's what you see on the skate rink, right? So if somebody was skating and you just came long after this and to see what is drawn on the skate ring, you would see something like this. So you'll get a front of this Legendrian, which was kind of somebody was skating, right? So, and in this dimension, in this case, you have a 3-dimensional space, and then you have again in 3-dimensional space, you have again front of our Legendrian curve, which if it's happen to be smooth, then it's a graph of some function. But if it's not smooth, it can't have a singularity. Okay, it could be similar singularity, maybe slightly more complicated, but that's what happens. And then we have a front. Okay. So let me kind of like immediately tell you some already, without going far away, you already can formulate some quite non-trivial question about this situation. Okay, so far what did I say? I say there are these context structures. Well, let me kind of summarize kind of what we say. We have a context structure. This is a non-integrable hyperplane field like this, and there is a what is called Darboux theorem, which says that locally all context structure in some coordinate look exactly like this, like given by this formula. So, like in general case, you get the kind of in high dimensional plane, you can write always form like this, but just locally. So globally, how it looks kind of globally, maybe you cannot find such coordinate as we will see. But locally, this is always possible. And then you have a tangent surfaces to this, and the tangent surfaces are called Legendrian curve or Legendrian surface or Legendrian, well, in general, submanifold. And this, our space, if you have you start function with n variable, you have the space is 2n plus 1 dimensional, and this 2n plus 1 dimensional Legendrian submanifold always n dimensional. This is the maximal dimension of possible integral submanifold. So now, remember I said that in the space, like you go in direction of tangent and you come to some different point, not in this plane. And in fact, what is kind of surprising thing about this non-holonomic mechanics, that traveling, if we have a non-integral structure, but traveling in dimension tangent to contact structure, you can come to any point, from any point to any point, which is like on skate ring, when you can skating and you can come any point and in any position you want, right? And so now kind of let's ask me the following question. So suppose, for instance, start with the following problem. So suppose I have want to find function which have a positive. So you start for your functions for say on interval 0, 1, and you want to find function such that derivative of this function is positive everywhere, and such that the function at the point 1 is less than at the point f0. So you started here and you want to come here, right? And you want to do it kind of having derivative positive. So this is difficult to do, right? So we study in calculus that it's not possible, right? If a derivative positive, then value on this end has to be bigger than value on this end. So question, is this property hold for general Legendrian curve? So that means that you have a front, and front would look just kind of like going like this, whatever. It's always going in positive slope that you want, but still you want to come to some. And of course you can come to any point, right? So just going, because you are allowed to turn and cusp and go with positive slope backward. So there are this like Legendrian curve with positive slope and kind of end there. So which means, in other words, what is it? Like how you can say it? You say, you take in our space, you take say x equal 0 plane in our contact plane and x equal 1 plane, right? And now suppose you are restrict to half space greater than 0. And you want to consider Legendrian curve in between 1 and 2, such that start in one plane and end on another plane. So question, is it true? And say this is a z coordinate. So what we say is that if it were graphical, then this z coordinate at this point have to be smaller z coordinate at this point, at the end. But for general Legendre curve, it's not true. But then the following amazing fact holds. So suppose you started with with any graphical curve in our space. So then for this graphical curve, end point are have to be one higher than another, if this is above. And suppose you deforming my Legendrian curve, keeping it all the time Legendrian, and what is important, keeping it embedded. So that means not allowing any self-intersection. And what this means? That means that during all deformation, different parts of fronts cannot be tangent to each other, because it's becoming tangent that at this point this y coordinate have to be the same, and therefore you get self-intersection. But suppose you do not allow this. So you have a deformation like what is called Legendrian isotopy, the deformation of Legendrian curve, keeping it without any self-intersection all the time. And then turns out that the curve which you get at the end still have a property that at the right end it has to be higher than the left end. So you never can get picture like this. So you can get picture which maybe look like this. Kind of something like this. So you get this front which have some all kind of cuspidal point, but what we'll see, and we will prove it kind of at some moment, that in this front you will always be able to find some kind of piecewise smooth piece which is is a graph of some continuous function. And because of this, because each piece have a positive slope, the value here will be value there. So this is already highly non-trivial fact, but we will prove it kind of probably tomorrow. Okay, so now let's move on. So we had this context structure, Legendrian curve, but now let's forget about z. So we started this function, added graph of derivative, and we get this context space. But now I just consider the space where there's only coordinate x1, xn, y1, yn. Okay, I forget about z. And then I take any Legendrian surface, and I project this Legendrian surface to R2n, like ignore z coordinate. Right? So that means that I'm just now consider graph. For instance, if I started with graphical function, so now I just consider graph of all first derivative of our function. So you get in 2n dimensional space, you have a n-dimensional subspace, right? Or like projection of this from there. So now question, what do we get? How can we, without reference to our kind of original picture, how we can characterize manifolds which we get by projection of this Legendrian back there? Turns out that they are so-called, so this space is kind of called symplectic, and this projection they call Lagrangian. By the way, there are all these words, Lagrangian, Legendrian, and of course you would think that Legendre invented it or Lagrange invented it, but all this was invented, all this word was invented by Arnold. So kind of like, of course, Lagrange you can find in the work of Legendre. In Lagrange you can find some kind of origin for all these things, but if you would ask Lagrange about what is Lagrange submanifold, unlikely he would tell you. So yeah, kind of Arnold really kind of he also defined Maslov index and kind of a lot of other things. Okay, so now let's kind of now try to characterize this. So now we are in 2n-dimensional space. So we are in R2n. And in this R2n, I want to consider, so in order to characterize, now I want to introduce something which is called symplectic form. So what is this? So kind of like, I think, like first shortcut to the definition would be the following. Let's think about our R2n as an n-dimensional complex space. So that means like every pair of x coordinate x1, y1, you think as a complex coordinate z1, etc. So you have a complex space, and so therefore, if you have any kind of vector, like, okay, so let's, like if you don't like complex spaces, just think about this plane. So you have a plane, and on the plane you have a multiplication by I, which rotation by 90 degrees. And so you take any kind of vector, v in the space, and you can multiply this vector by I. You can multiply this vector by I, and then this you rotate it, you get a vector which is orthogonal to original vector. Also, I can think about Cn as a standard Euclidean space. You have a standard dot product. So if I have a kind of some vector z and I have a vector z prime, I can take kind of dot product of these two vectors, kind of standard scalar product. So this is the scalar product is well in the plane. Therefore, you take z times z prime times cosine the angle between them. But now I want to multiply one of them by I. So I take IZ and this one. So I take one vector first, multiply by I, rotate, and after that take a scalar product. So that the result will be you get exactly the same thing multiplied by sine. So when you multiply by sine, the z times z prime, this is of course just area of this parallelogram. So what you get? If you have a x1, y1, you multiply by vector by I in real notation, you get minus y1 x1 vector, and then you take a dot product with this one. Yes, so well, what I'm writing, you have a you take the dot product with this one, so you get x1 y2 minus x2 y1, so you get this determinant of these two vectors, and this is precisely area of this parallelogram. So this is called symplectic form. So this is a bilinear form, which is a skew symmetric. So kind of it's in fact it's not area, but it's sign area. When I change its area when the orientation z prime coincides with orientation point minus area otherwise. So you have a skew symmetric form, and this skew symmetric form is the area form. So now, what is like? We have this submanifold. Let's call it LF, given by this thing. And turns out that this submanifold, you can easily compute it, has the following property: that if I take a tangent space to this submanifold at any point and multiply it by I, then it's becoming orthogonal to itself. So you see, it's not necessarily if you take on the plane, if you take a line multiplied by I, it becomes orthogonal to itself. But in 4-dimensional plane, there are some plane, for instance, plane x1, y1. When you multiply by y, by I, they are becoming the same plane. You just rotate the plane. And if you take a plane x1, x2 multiplied by I, you get orthogonal to itself. So there are some plane which is kind of like, you get all scale. Like if you take multiply plane by I, you can get kind of any angle with the original plane. And if this angle is pi over 2, is orthogonal, then it's Lagrangian, and this is equivalent to this one. So now let's kind of we just introduce this definition. We said that you have a space, you have this R2n. In R2n, you have this symplectic form omega, which we define this way, and n-dimensional subspace in this R2n is called Lagrangian if you have this condition that ITL orthogonal to TL, which is exactly the same thing as to say that omega restricted to TL is equal to 0. So that means for any two vectors, z prime, which are tangent to TL, omega of z prime is equal to 0. Right? Because when what? No.
You are multiplying by L or tangent space?
Tangent space. You take ITL at any point and it becomes orthogonal. So I am not allowed, from the very beginning, I allowed my L to be not linear. It was a graph, just anything. Okay, so what are Lagrangian summations? So let's kind of explore what are Lagrangian summations. So first of all, let's take a two-dimensional case. So R2, what are Lagrangians? So Lagrangian submanifolds R2 are one dimension. So just any curve, of course, Lagrangian, because you multiply by I, you get this one. Okay, so in our R4 already kind of is pretty restricted. If you take a R4, which is kind of the same as C2, then as we see the one example of submanifold, you take any function and you take a graph of first two derivatives of this function, you get Lagrangian submanifold. So there are non-graphical submanifolds. For instance, you write like Z1 is equal some modulus is equal A, and Z2 is equal B. So you take a circle on one plane and circle on another plane, and take a product. So that you get a torus, which is automatically Lagrangian. So it's called product torus of this one. So we'll see many other Lagrangians. So this is kind of very interesting object and kind of important to understand what are these objects are.
So you were calling that a graph LF of the derivative. You are not taking x.
No, this LF is just given by this equation. So it's a set of points x1, x2, xn, df for dx1, df for dxn. Yeah, right. So it's of course it's like when you have a graph of function, you say this kind of you write y is equal f of x, right? So it's a set of points x f of x. Okay, so let's consider the following question. Let's consider transformation. We want to consider if you take a okay, maybe it's already time for me to really to speed up slightly. Okay, so I was so far we were talking about geometry in Euclidean space mainly, right? But it's kind of convenient to slightly extend class of like objects which we're working for. So I don't want to really go to a general simplicity contact manifold. That will be not so kind of important for my class, but slightly more general thing useful. So for instance, given kind of like, okay, now if you don't know this, don't ignore this. So I mean, suppose you have any n-dimensional manifold, right? And then with any dimensional manifold, you can associate its cotangent bundle. So cotangent bundle is a set of all kind of linear function on tangent spaces. So this cotangent bundle, for instance, for the case of Rn, cotangent bundle just naturally just a sub to n. So it's a twice more dimensional space. So cotangent bundle has some kind of God-given one form differential. So usually in kind of like mechanics, it's called form PDQ. So this is a form which is like if you think, so the cotangent bundle in mechanics has a meaning of phase space of a system. So you have a M as a configuration space, a cotangent bundle is a space of point plus, well, you can say velocity or dual object momenta, and this is called cotangent bundle. And then if you take any vector tangent to cotangent bundle, then there is a form kind of alpha such that value on the form on this vector is the following. You take this vector, project it to the base, and this point itself is a linear function. You can just evaluate it. So it doesn't matter if you don't know, but important that in any local coordinate it's have this pi dqi form. If you take any local coordinate on the manifold, this is form. So anyways, there is some form. If you can by some reason not like this, just forget. Euclidean spaces will be kind of mostly enough for whatever I say. So we have a cotangent bundle, and cotangent bundle has one form, and differential. Oh, sorry. How can I clean this? By what? I don't want to destroy this. Okay. Okay, sorry. Yeah, that's you know, when I was like, I started my pedagogical career, kind of like first was teaching like in university, and was some old professor, and he said, well, you can, like after each lecture, you should look at your hands. If both your hands are in chalk, that means it was a very bad lecture. So like if it was a good lecture, one hand should be always clean, because if you have both are dirty, that means you're writing with one hand and erasing with another, and you never should do this. But I know I do even worse. Okay. So okay, so you can kind of generalize whatever I said instead of Cn to this cotangent bundle, and there is a object which is a cotangent bundle. So you can think that cotangent bundle is a space holder for all differential or like all collection of first derivative of any function, and if you add one more coordinate, this is called one jet space, and this is a like space where you can draw simultaneous graph of function and its derivative. And this one has this canonical contact structure which you can write by this dz minus pdq is equal to 0. So, but let's return. Okay, let's return maybe to Cn. For a while, I still good with Cn. and R2n. Let's consider what are transformations. What are transformations which preserve symplectic structure? So what start maybe with this Riemannian with Euclidean case. So suppose you have a scalar product. What are transformation of the plane, for instance, which preserve geometry, which preserve scalar product? So in principle, of course, linear transformation just orthogonal transformations, rotation of reflection. But if you allow even nonlinear transformation, then if they preserve geometry, they still not very much different. They can be, in addition to rotation and reflection, you can also have a parallel transport, but nothing more. So any transformation of plane which preserves geometry, scalar product, is in fact rotation around some point or reflection around some line, not more. But now, in the case of skew-symmetric symplectic form, what are transformations which preserve symplectic form, which mean which preserve area of any parallelogram? So this is a kind of turns out to be huge kind of like what is called group of transformation, because it's just any transformation such as like Jacobian of the transformation is equal 1. So the condition that you take a like you started with something, and kind of like the shape of any domain can change, but the area of any domain, whatever you take, area of any domain remains the same. So it's a preserved area of any domain, but not its shape. So this is the kind of area preserving transformation. So this space or group of all transformation is extremely huge group, and we'll see like in a second why there's so many of them. So now you can go to high dimension and say, like in dimension 4, what is a group of symplectic transformation, so transformation which preserves symplectic form. So there is this kind of word in this subject called terrible word called symplectomorphism. So this is a really terrible word. So it's a, first of all, this is a kind of very bad term, because it, well, first of all, the symplectic already kind of strange thing. It was the name invented by Hermann Weyl, and it combined Greek and Latin root, like from complex and like symposium, kind of like together. So there's a so simplect already Greek and but now this is a like semi-Latin, and this is a Greek, and so this is a kind of like complete nonsense philologically, but that's what the term is used. So it's a transformation preserving symplectic structure. In mechanics, they call canonical transformation. It's also not great name, but kind of. Okay, so in the two-dimensional case, the symplectomorph is just area preserving transformation. But in dimension 4, they are kind of much more mysterious. As we'll see, it's kind of not so easy. They turns out to be also volume preserving, but they are much more restrictive than that. So now let me kind of introduce one more kind of like instance where this Lagrangian submanifold arise. So suppose, for instance, I take R2 and I take area preserving transformation of R2. And now I want to consider graph of this transformation. So for instance, this f of xy was given like, let me write x capital and y capital, this coordinate function. So the f of xy is equal like x capital of xy and y capital of xy. So you have a two coordinates. And you just consider this like x1 and x2, and here you have a graph of this transformation, so you just write x2 is equal x of x1 y1, and y2 is equal y of x2 y1. So question, is this graph simplex Lagrangian or not? Again, obviously not. Kind of like, but I kind of slightly have to change something. So for instance, I change my symplectic form by putting this, my original symplectic form, and here changing sign of symplectic form. For instance, I combine my graph with reflection in this plane. So then it's becoming symplectic Lagrangian, because what does it mean? What does it mean that it's area preserving? That means that if I take any two-vector tangent to the graph and project it to this plane and project to this plane, area will be the same. But now I change sign, so they like we take a sum this plus this, I get 0. So therefore, you can think about this another instance of Lagrangian submanifold of graph of area preserving transformation with this small nuance of changing sign. So now let's consider the following question, and I'll explain why you want to consider this question. So suppose you want to study fixed point of some area preserving transformation. For instance, there exists this famous problem which was formulated by Poincare. He said, so in 1911, I think, he wrote paper, kind of which was a dramatic paper, which said, I'm extremely old and kind of probably will not be able to finish this work, but this is very important work. And so first time in my life, I published paper with unfinished thing, but for many years I tried to prove it, and I consider many special cases, but I still couldn't prove it. So he was not so old. He was actually 56 years old, but but he was sick, and he actually died soon after that in a few months. But he was kind of formulated the following question. So you have an annulus, and you have an area preserving transformation of this annulus. And this area preserving transformation has the following properties, that it twists one boundary by one direction, another boundary in another direction. It's not immediately clear what does it mean, because if, say, for instance, a twist by 180 degrees, how to know in which direction it twists. So in order to say it kind of more precisely, you have to kind of look, instead of transformation of annulus, go to transformation of strip covering, and then it's kind of unambiguous. What does it mean that it moves boundary point in different direction? And then it says, in this case, it must have at least 2 points which are fixed by transformation. And why he wanted to say that? Because, in fact, some problem in like classical problem of like so-called restricted three-body problem about periodic orbit can be reformulated to this question.
You mean to say this transformation is area preserving?
Yeah, yes, area preserving. I didn't say it. Okay. So if the area preserving transformation, of course, without area preserving transformation is obviously wrong, because you can just you do transformation and then you say shift every point like toward one boundary component, and you get rid of all points. Okay. So now I will prove this theorem today later, and question how to so what was the argument of Poincare why this should be true? He said, well, you can reformulate this question. So let's again I will explain technically how to do it. But you have this is given on annulus, but I want to change to some transformation of plane. So I'll tell you how to do this. But you get some transformation of the plane, and then in this, you take a graph of this transformation. And fixed point of transformation is intersection of the graph with the diagonal, because diagonal is a graph of density. So our fixed point is this one. So if my diagonal, my graph, is not very much different from, not so big, then it's kind of like you can try to find such system of coordinates that both of them graphical. But if both of them graphical, then it looks like one graphical. So this is a coordinate x1, y1, and x2, y2. But suppose you manage to make them graphical and like some coordinate where projection to Lagrangian plane, x1, x2, and y1, 2. So then it has to be, as I said, graph of simultaneous graph of first partial derivative function. And in this case, intersection point will be point where two functions have the same first partial derivative. That means the difference of this function have what is called critical point. So this is a problem about finding critical point of some function. And then you analyze some boundary condition for this point, and turns out that in this case it reduced to the following problem. You have an annulus, and on annulus you have a function, and function like this conditions that move different direction translates that on one side of annulus gradient is put inside and another also inside. So this function grows as you go, like it's constant on the boundary, and grows as you go from boundary inside. And of course such function must have critical point, because at least it must have a maximum. But then we can also argue it must have a saddle point, so it has at least two critical points. And but then it only holds this argument, it only holds if transformation not too far from diagonal. But what if it's too complicated? And so Poincare considered like hundreds of special cases. What happens? So he was drawing a picture like if it's not very much deviate from the diagonal, so that means that if you consider, for instance, one of vertical intervals, that image will be something like this. But okay, so suppose it's not like this, but kind of like this. Or suppose it's kind of like, it's okay. So he tried to classify all these cases, and of course kind of like you can classify all of them, though it's possible. So now proof known exactly this way. Okay. But turns out that his original idea about functions kind of still work in this case, and I'll explain how to do it. So let's make a break right now. So I kind of like in some sense can forget about whatever I was telling you before, because I will be just kind of start proving the theorem and kind of just explain how to relate.
There was one statement that you made about Lagrangian manifolds, which are embedded. What was the precise statement I think, right? About this monotonicity that you can find a piecewise continuous.
Yes. About Legendrian, I was saying. So if you take any Legendrian curve, then kind of like there is no much constraint you can, for instance, find about this. But if this Legendrian curve is Legendrian isotopic to graphical one, then turns out that it, like though it's not graphical, then it preserves many properties as if it were graphical. And I will explain in precisely what it means. Okay.
We have P outside.
So So this is, as I said, last geometric theorem of Poincare. What it precisely means? So it means the following thing. So you take a the area preserving transformation of the annulus, and instead of annulus, you just go to covering map. So you take the strip, and on the strip you have a transformation which is like equivariant with respect to shift by 1. So if you shift x by 1, then the resulted first coordinate shift by 1 in this one. So you have this transformation, and you know that top boundary, every point move one direction, another moved another direction, and then the claim that there exist at least 2 points. Of course, 2 points mod 1, so that means that this point kind of repeated infinitely many times. So this is the theorem of Poincare, and which I will prove. So, but before going to this proof, let me kind of like tell a little bit of history of this. So it was, as I said, formulated by Poincare. He provided some motivation for this, which, as I said, coming from some problem from celestial mechanics. And then he gave some argument for one cases and kind of how this he think could be done. And then, but he didn't do it. He died. And then, few months after his death, Birkhoff proved this. But unfortunately, Birkhoff found very clever proof. So he found very clever argument, which kind of proved the theorem, but it was a complete dead end. So it's proving the statement, but there is some kind of like Poincare, in fact, had in mind this not as a kind of standalone theorem, but he obviously just wanted to say that it's a kind of like example of something which kind of he need to be kind of understood more generally, and kind of, although he didn't formulate anything more generally, but obviously the way how he talked, that's what he wanted. But what Birkhoff did was some kind of argument was extremely specific for this case, which really didn't work for anything else, kind of like what. And so it was, as I said, in 1912 when he proved it, and then for at least 55 years, nothing was going on in this area, like no kind of was no development at all. And only in 1965, Arnold formulated some conjecture, kind of like he was obviously frustrated by state of the art was going on, and he formulated kind of conjecture. And this conjecture kind of essentially, I will not formulate precisely because it will not be important, but maybe later. But they essentially was saying that the theory of fixed point, not only for area preserving transformation, but in high dimension for transformation preserving symplectic structure, it should be governed not by just pure topology, like for without this condition that they symplectic preserving, but should be governed by theory of critical point of function, which is kind of known to be as a Morse theory, which kind of more subtle topological theory. So that was this kind of essence of Arnold conjecture, which was saying that this argument which Poincare gave actually in this paper for small transformation, where you really can reformulate question about fixed point as a question about finding some critical point of some function, this kind of relation in some form should hold in kind of in general. And that's what kind of like this my kind of lecture course, which during this week should be kind of explaining how this idea was realized, and kind of so what we have. Okay, so I will kind of go to the proving it, but before kind of I need to formulate it in a little bit more general case in order for this to make sense. And I need a little bit more of basic notion. So you have a, so suppose you have a, like, okay, in general, you can think about symplectic manifold, but like it's completely sufficient for purposes what we're doing today, that we have a just, we're talking about R2n, and kind of like you have a, this standard symplectic is a standard symplectic form as I defined. And then I said there are plenty of symplectic transformations. So how do I know that they're reflexive? For instance, why there are many of them? First of all, because there exists the following notion of what is called Hamiltonian vector field. So suppose you have a vector field in R2n, and vector field, at least locally, always define some one parametric group of transformations. You can integrate, define some phase flow. So given vector field, you can define flow, which is kind of like you take every point and you just solve. You consider so you consider this dvt at the point x over dt. Kind of you want to find flow is equal vector v at the point this vt of x, right? So you can consider this, try to find integral trajectory of this one, and this define a phase flow. So there's a phase flow, and now I'm asking when the phase flow preserve symplectic form. So when you have this, like if you take a, like, okay, we said pullback of this omega is equal to omega, which means that like this transformation which forms this flow consist of symplectic transformation. And then this is a, okay, so in terms of standard, you know some basic kind of like, yes?
Here, so this 2 fixed points, so I mean, why 2? So does there exist example which has exactly 2 fixed points?
Yeah. Yes. There exists. Okay. This example will happen in 1 second. Yeah, but when I finish saying this one, it will be example. Okay. So, okay. So you have this v, and now the question. Yeah. So I'm asking, is it okay? I kind of you will be using standard, like, I don't know, Lie derivative and this kind of thing, or is this not so good? Not so good. Okay, fine. So we have so we have this condition, and we want to understand what this condition means. And this condition means the following thing, that that if you take a form omega, so I'm saying this condition, and this is a kind of, okay, I will maybe come, maybe in the afternoon we can come and just work it out, this one, but this condition that this t star omega is equal omega is equal, you can reformulate the following way. So you take the form omega and take a contraction, say what is called interior product of omega with v. And what you want that this thing is closed one form. So you take, so omega is what is called differential 2 form. And if this differential 2 form you plug instead of first argument your vector field, that's called contraction. You get differential 1 form. And this differential 1 form have to be closed, and this is what symplectic means. Is it okay? Or we should kind of elaborate on this? You just tell me, because if I need, okay, maybe we'll kind of work it out. But there is a, so this is called, so if this is closed, this is equivalent to the fact that it is that it consists of symplectic transformation. but sometimes closed form exact. So that means that this is a differential of function. And if this is a differential of function, then it's called Hamiltonian vector field. So of course in R2n, closed and exact the same thing, and so therefore there's no kind of difference between the closed and in this one. So maybe you can even ignore this, but just say the following thing. So what is Hamiltonian vector field? You take a function, and now you take a gradient of this function. So gradient of this function is a, okay, like in this notation which I would use, is a dh over dx and dh over dy. Right? So if you have a more coordinates, that means dh over dx1, dh over dx2, dh over dy1, dy2. And then remember what was our form. Our symplectic form was a scalar product twisted by I. And so now what I take I twisted with a, rotated by this one. And I will call this xh. And then turns out that this, so what it is? It will be minus dh over dy, dh over dx. And actually, I think I want minus. I take minus this, and then I have a plus minus. I want this. So I consider this this vector field. And so what is this vector field? So if you have a function, you take a gradient of this function, and now you rotate it so you get some vector field which is tangent to the level set of this function. And this is called Hamiltonian vector field. And precisely this is the same as this. So if you take a interior product of vector field with omega is equal to dh, that means that v is equal to this vector field. So just that means, nothing else you need to know. Okay, so there are this vector field, and so if you have such vector field and you consider flow of this vector field, is preserved symplectic form. So that means it implies there are kind of really enormous number of area like in two-dimensional case area preserving, in high-dimensional case symplectic transformation. So that means that you take any function, and this function give you. And moreover, this function need not to be like, it's also can be function also of time. So that means that you can, at every given moment, you can flow in kind of with a different function, and all this will give you this symplectic transformation, symplectomorphism. So clearly there are many of this. For instance, this fact by itself already implies Darboux theorem, because of course you can have suppose we have this kind of some symplectic form, and suppose in our space we have any 2 points, and you connect them by some path, and then take a just piece of hypersurface containing this path, and such that at every point of the path tangent plane to the surface is yes. Yeah, just take this. Take any such surface, and then take any function for which locally, which this surface is a level set. And now consider corresponding Hamiltonian vector field. The Hamiltonian vector field gradient will be orthogonal. So when I multiply by I, you get a tangent to this one, and so therefore you get a Hamiltonian flow which given curve will be trajectory. And so therefore when I flow neighborhood of this point, it becoming neighborhood of this point in time 1. and then that means that these two neighborhoods are equivalent. There is a transformation which send one another. Okay, anyway, but this is a side remark. But in any case, so there are plenty of this transformation.
But this would be like half of Darboux. Let's say that what if you have a different symplectic form?
But it's almost Darboux. Okay, so here's what correct thing. So the correct thing will be the following. So how Darboux theorem? So the Darboux theorem says, okay, so I didn't really define symplectic form in this way, but if you have it's also defined closed non-degenerate form. So then if you take one symplectic form here, and suppose here it's standard one, and here is another one. And now we think that this is a two neighborhood on Cn. And now statement first that we can find, if you connect them by path, we can always find non-degenerate two form extended to this path. And after that is this argument. Okay. But yes. So as I said, in the case of R2n, there is no difference between Hamiltonian and symplectic, because there is no difference between closed and exact. But for instance, if you take not R2n, and as I would in the second, I take a torus. So I take a kind of, say, quotient R2n over kind of Z2n, right? So I just quotient by kind of like, for instance, I take a plane and quotient by translation by 1. So you take and then I would like to, and then I take of course you get a symplectic form there. And I would like to define Hamiltonian vector field there. So then not every symplectic vector field is Hamiltonian on this one, on this quotient. For instance, suppose you have a torus, two-dimensional, and just start to rotate torus around themselves. So then, take a translation. So that means that corresponding form will be just kind of dx. And this form dx, when you project to torus, will be like dphi form on the circle. It's not closed form, but not exact. And so therefore, there is a big difference between this. And so I don't want to go into. I actually I will have to say something about this later, but right now it's not important. Okay. So now I can formulate this Arnold conjecture, which was called, but this statement which, as you'll see, generalize the theorem for other manifold, and in particular for torus. So let's start with two-dimensional torus. So here we had this annulus, but now I take a torus, two-dimensional torus. And now I have a f is an area-preserving transformation of the torus. And I would like to say when area-preserving transformation of the torus have a fixed point. And then, so kind of similar to this thing. So it's not true that any area-preserving transformation of the torus must have fixed point, because it kind of should be some kind of analog similar here as boundary twist, because otherwise I could kind of take here annulus also. I take a torus and just rotate over itself and will be not. And this can be corresponding condition can be formulated equivalently, and it's not obvious that equivalent, it's kind of like theorem, in the following way. So suppose that so one of the following equivalent condition holds. F is, I will call Hamiltonian. what it means Hamiltonian, it's what I defined. That means that there exists maybe time-dependent Hamiltonian such that time one map of this time-dependent Hamiltonian give me F. 2. F is okay. I say that as Arnold said, F preserve center of mass. So what that means that F preserves center of mass? So you can, because it's a transformation on a torus, again, you pass to covering transformation of the plane. So on the plane, there exists kind of lattice, which gave me this torus, and there is some fundamental domain of the torus, right? And under my transformation, this domain is kind of mapped to something else. So the image of fundamental domain and the transformation give me some other disturbed domain. And this domain, because there is an area form, I can compute center of mass of this domain. And I want center of mass not move anywhere. So the preservation of center of mass does not mean that any point is preserved, right? Because it's a center of mass is not kind of image of point. So preservation of mass just means that kind of mass, center of mass, kind of at this domain the same as the original. That's Arnold kind of way of formulating this. So there is a kind of another equivalent formulation is the following. So you take on the torus, you take any closed curve. And then you consider, so first of all, this transformation which I consider, I want to be what is called transformation which are homotopic to identity. Kind of like, so that means that so if I take every curve, every loop, then it mapped to some loop which is kind of like can be deformed back. It's not kind of like, for instance, width.
The choice of the fundamental domain is not unique. So this is independent of choice
of a fundamental domain, of course, needed, but this is independent of the choice. But of course, when it's said preserve, it's also preserved up to action of the translation, because the choice of covering map is only preserved to this one. So now you take a point and take an image of any loop, and because these two curves are kind of in the same homotopic class, then there is some annulus between them. So there is one curve and there is a kind of annulus, the another one. And you can consider some kind of deformation between them. And you can pull back my area form and integrate over the annulus. So you can compute algebraic area between curve and its image. This is called flux. So the kind of value of flux of any loop, you have to be equal to 0. This is exactly equivalent to the same preservation center. And there is another fact which completely unclear why this is true, but there is another third definition which said this is equivalent to the fact that this transformation is belongs to commutator of the group of of identity component of the group of area preserving transformation. So that means that you can present this as a product of commutator, but doesn't matter. That's called the theorem of Banyaga, who proved it. Yes?
How are you choosing
Choose anyway. It's kind of independent. Because, okay, so this, maybe this condition is kind of like probably the clearest, right? You take a loop, take its image, and consider what is the area between them. And you want to be 0. So you don't want to kind of like loop, kind of shift it and have some positive area between them. If one part of loop one direction, another have to.
No, but if it happens like the picture below, then there is no clear area between those two loops.
Yeah, but what is, because there is a homotopy, and what is homotopy? Homotopy is a map of cylinder. So for every loop, there is some cylinder which is connect original loop with its image. And so you can, over the cylinder, you can integrate area for.
And this last criterion that you said was it's in the commutator subgroup of all symplectomorphisms?
Of all commutator subgroup of the identity of symplectomorphism, but which are in the same component.
Maybe I missed it, but I would like to ask this. So you have this Poincare's result where you have boundary conditions, and then you suddenly go to it being Hamiltonian. So how did Arnold come up with this condition to replace the boundary condition so that 2 points are ensured to be fixed?
Okay, you can, in some sense,
because that seems to be quite a big jump.
it's not big jump if you know the proof. Because but I mean, but when Poincare had this proof, right? And there he used kind of like function. And he needed to get function, not closed form. And so Arnold wanted to kind of imitate the same proof in this case. And the same proof works kind of word by word for small transformations, as we'll see. But again, you need some condition which. Yes.
So if it's not a Hamiltonian vector field, but a vector field which is symplectic, is there a canonical origin there? Something like a Hodge theorem by which you can pull it back and reduce it to a Hamiltonian vector. So replace the one form by the one form minus the harmonic representative, for instance, or is there some other canonical representative?
Yeah. Okay. So there is this like called Novikov theory of kind of like so. So there is a kind of version of all this thing for closed case. Yes, but okay, let's not go. Okay, so now like first, okay, so like whatever you, so I will be using the just Hamiltonian, we will be proving the Hamiltonian definition. But now I just want to first explain how you reduce case Poincare theorem to this one. So why? So suppose I will be proving say case for torus, and now question how original Poincare theorem would follow from the torus case. So you have this, remember we had this annulus which I interpreted as a strip. So you had a transformation of the annulus. And now I want to extend it to torus. And of course what I will do, I will kind of, so now I kind of like take a whole plane and I just slice plane. So we already have this kind of lattice, but just kind of rank 1 on this one, because this our annulus was a quotient by this translation by 1. But now I want to extend this one. So I already have this transformation f on the strip. So how to extend it to the torus with the condition that it is Hamiltonian or the preserved center of mass. So what you want, you take this transformation, and first you can what you would like to just double it with inverse sum, kind of reflect and extend here, right? But this not quite working, because how do I know that this area cancels this area? So you need to have some kind of insert connector. So you put the strip, but put some kind of like small strip inside. And now suppose, for instance, first I just double it. But suppose now I look and I see the area do not cancel. For instance, this area is slightly smaller than this area. Then here I just push them a little bit further here to have in such a way that now this area is exactly the same as this area. Or maybe this area is bigger. Then I kind of push this a little bit in this direction. So by this kind of adjusting in the strip, I can arrange this condition of preservation of mass. Okay? So this allows. So again, if the both directions were kind of moved in the same way, I would not be able to play the streak because kind of like because in order to compensate, I would create extra critical point, which are not. But here, I would always pushing the same direction, so therefore I'm not creating any extra fixed point in this strip which I connected. Okay. So this is a reduction. Okay. So now let's start proving. So we have our so now we have this. What we have? We have a transformation, area preserving transformation, and I will be proving for two-dimensional case. But in fact, the way I am proving will be working in any dimension. You could replace this instead of R2 or R2n, and it's preserved symplectic form, and proof would work kind of word by word the same. So, but let's keep R2. So you take this kind of like R2 to R2, and this is like equivariant the transformation kind of with respect to like action of lattice, and you have this preservation of mass or whatever condition, Hamiltonian condition. Okay, so now suppose. So now let's consider. So we have this coordinate. So you take this R2 and like take a product. So take a graph of this. So you take a R2 and I will write R2 bar. R2 bar meaning that I change sign of symplectic form. So here you have a form omega, and here you have a form minus omega. And now I take a product, and in the product I have our graph and the diagonal. So called diagonal D. That means that this is a x2 equal x1, y2 is equal y1, and you have our graph. So that means that let's call it gamma f, and gamma f is equal, okay, x2 is equal, I will write x1 and plus some small extra thing, plus alpha, and then maybe y2 is equal y1 and plus some beta, where alpha, beta, some small function, small addition. So you get this one. So my fixed points are precisely intersection point. But I want to treat this intersection point as a critical point of some function. So which function? Where can I get a function? For this, I need to find some kind of splitting of this splitting of the space into some into some Lagrangian splitting in order to see. So you consider the following thing. So consider plane. So here is this coordinate x1, y1 in this presentation, and x2, y2. and the like symplectic form. Okay, so let me draw this as dx1 dy1 minus dx2 dy2, right? Kind of like, okay. So it's a difference between these things. So now you consider coordinates. You consider coordinate x1, y2, and x2, y1. Let's split this way. So notice the diagonal is a graphical in this coordinate. Because what is the diagonal? Diagonal x2 is equal x1, y2 is equal y1. So instead of this, I can write it's equal y1 is equal y2. Right? It's the same thing. So therefore, it's a graph of this map. So diagonal is a graphical in this coordinate. And because our graph is not very much C1 close to diagonal, therefore it's also graphical with respect to this splitting. There are some function, maybe alpha tilde, beta tilde, such that in this new coordinate is a graph. So therefore, because they are graphical, they are both graph of derivative of some function. Question of which function? So this diagonal D, it's a graph of derivative of which function? So there is some function such that D is given by condition x2 is, so you take a x1. So I want, I think, y1, so y1 and x2. So I claim that there is some function such that it's given x2 is equal, x2 is equal d of f, say maybe f, like d of h, with respect to d of, with respect to, so here I wanted, so what actually can I can write that my my form is a d of x2 dy2 plus y1 dx plus y1 dx1, right? Maybe, okay, maybe sign is wrong, right? Minus this. So up to sign, it's a differential of this thing, right? And so therefore, now if I take a x2 is equal dh over, so I want that it equal dh, x2 dh over dy1, and y1 is equal dh over dx1. So I want some function of this variable x1, y2, such that if I take a partial derivative of this function, then I get precisely this. So what question? What's the function h? Answer: h of x1, x2, y2 is equal x1, y2. Right? If you differentiate it with respect to x1, you get y2.
Sir, actually,
We got the
What?
that will be del h del x2, right?
So
No, that y1 equal to del
I
h.
think y2 equals.
y1.
Next line.
That's just
next line x2 equals del h.
Then
by
y2 equals.
Yeah,
y2 equals.
So y2 equals
y2 is equal. So what here? If you take a gxy1 with respect to y2, yeah. So with respect to dx1, this is equal y2, and if you take a dh with respect to y2,
that is del
x1.
X1.
X1. Okay. 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 So you get this, right? So this is this function, and now what we get. This is for the diagonal, and for our transformation you have to add something. So it will be function x1 y2 and plus some small function. Let's call it phi plus some function. Right? So now this so this function, yeah. So you have this function, and I'm interested when partial derivative of this function is equal partial derivative of this function, which means that I'm interested in critical point of function phi. And now the question, where the whole this my fight with Hamiltonian or not Hamiltonian, where it's, because so far I only use the fact that it's Lagrangian, which would be true for any area preserving transformation. But now this function phi is a function on the plane. My Lagrangian is a periodic, but it's kind of derivative. But if derivative is periodic, then the function need not to be periodic, because over each period it's only periodic if integral of derivative over period is 0, right? And this my claim that this condition that it's Hamiltonian or preservation of center mass exactly guarantee that this function phi becoming periodic, not just periodic with plus adding constant, but honestly periodic. Which means that function phi is a function on the torus. And of course, function of the torus must have some critical point. At least have maximum, have a minimum, and in fact, more points. So you know that like there is a Morse theory which says that on the torus, say if it's a Morse function, then it must have at least 4 critical points. And so in this case, therefore, this transformation must have at least 4 points, if not degenerate case. But if you do not assume that it is a Morse function, then in fact you can always collide 2 points to 1, so you can make 3 points. If degenerate point, you have a 3 point, but no less than this. And so therefore, so this is proof, the theorem, in the case when when transformation is small. Yeah, and this is a essentially repeat of the argument of Poincare, which was given for the case of annulus, and this was motivation for Arnold why he wanted to have this conjecture and why this condition came, right? So that precisely we need this periodicity of this. Okay, so now fun question: how to now what to do? So we would still like to treat it the same way. So we would like to be able to find some function and deal with critical point of the function. And now there is this kind of like solution which came here, which kind of like there was a it was a long development. So this was a kind of like proven. Okay, this like I proved this kind of I gave. I would say wrong proof in wrong philosophical sense. Wrong proof, it's correct proof, but wrong proof kind of which still did not allow to generalize to high dimension. But kind of like the proof which kind of immediately generalized to high dimension was first given by Conley-Zender in '82, and then it was some kind of version of Chaperon and kind of some other development and some kind of argument of Guyental. But so what I'm explaining to you, some result of some understanding of what development coming after 1982 paper of Conley-Zender. So, and the point is the kind of the following. Remember, I drew you this picture like at the very beginning. So, like Poincare when you have an area preserving transformation, you can consider this transformation which, say, look like this, kind of like regular, take every, say, straight interval map to something, and which is not too complicated. And this is essentially equivalent to this condition.
So there is some kind of an index sum going on in higher dimensions in general?
You'll see. Okay. So in principle it look like okay, but what if it kind of look like this, some kind of like whatever. So it's completely as far from graphical as possible. So kind of like how you deal with this. But then there exists, turns out, the kind of like the idea what I'm going to explain is I would call it trading dimension for complexity. So turns out that kind of like something extremely complex, like in two-dimensional plane, like this curve, like winding around, like intersection. You can understand an intersection of something of graphical, but of much bigger dimension. So what actually going on? So we will have some kind of like something, and then something graphical. But these two objects will be of high dimension, not of two dimension, but high dimension graphical object, and they will be almost tangent. And therefore, you see, if you have almost tangent surfaces, their intersection could be fantastically complex, right? So like imagine that you have, say, plane, and then you kind of draw some kind of curve which very complicated. And then you consider function which say positive, but this curve say divide our plane by two parts. So I can take some positive function here and say negative there. But this function itself can be very small, can be multiplied by epsilon. The function is almost zero, kind of like. So it's close to zero. But nevertheless, when I consider like where f equal to 0, this equation defines something fantastically complex. And that's what will happen in what I'm doing. So now you do the following thing. Okay, I bet. Just 1 second. What? Okay. Yeah, of course, exactly that's the idea. You're absolutely right. So the like when you kind of like already said that it looks like obvious thing to do, but kind of it's not obvious. Because for many years it was not obvious. Okay, so indeed, so you have some our Hamiltonian isotopy, right? Our transformation is Hamiltonian isotopic to identity, right? So that means that you can say the time one map of some deformation, but this time interval from 0 to 1, you can take some n and take a split, so you take from 0 to 1 over n, from 1 n to 2 over n. So you can present this f as a composition f1, f2, f3, and etc. fn. And each of these things is a small Hamiltonian deformation. But composition of them already not small at all. So you get this one. But now you play the following game. So you consider this now the following thing. So take the following product. So take R2 and take a R2 cross this R2 R2, well, this bar. Okay, I will write is this one. And here I can find graph of F1. It's live in this one. Then I take a R2. Okay, so let me just do it for the case 2, but kind of the same argument in general. So I take another copy of R2 times R2, and here you have a graph of F2. And now you take a product of all of them. So you have here omega minus omega, omega minus omega. So you have this thing, and now take a product of these two. So this is, again, big 8-dimensional symplectic space. In this big L-dimensional symplectic space, there exists Lagrangian surface, which is a product of these two graphs. But there are some, so now I want to understand where's my fixed point in this case. So we have also some diagonal. So kind of what diagonal you have? You have a diagonal. Okay, you can take this diagonal. So let me call this diagonal delta 1 1 bar. Then you have also diagonal delta 2 2 bar. This diagonal here. But then you also can take a diagonals here. And this diagonal, you call it delta 1 bar 2 between. But then you can cyclically take diagonal there, which I call delta 2 bar 1. So this is this diagonal 2 dimension and this one. So now we can take a product of these two diagonal. So you take a delta 1 1 bar times delta 2 2 bar, and let me call it even diagonal. So I call delta even. So this is again Lagrangian subspace in the space. And I can take a product of two other diagonal. So I take a delta 1 bar 2 times delta 2 2 bar. And I call this delta odd. And if you have more of them, I play the same game. I take product of this, a product of this. 2 bar 1, yes. So you take this thing. And now my claim is that fixed point of the map F2 cross composition F1 are in one-to-one correspondence with what? With intersection of the graph of this F1 times graph F2 with delta odd. So in one-dimensional case, you kind of didn't see this because this even diagonal odd is the same thing. So you took this one. So now this is a kind of why this is true. So it's kind of like it's a pure like set theoretic argument, right? So you see, what does it mean that F2 F1 of x is equal to x? And so it means that what it means you need. Okay, so the fact is here that means that it's point x f of x. Then intersecting with this one, you equate second coordinate here with first there. And then again you take this coordinate, map it by f, and then equate this with the first, and this is exactly means that you have fixed point. So this is a kind of so okay. So now, but now because these are all small, the product of this thing is you can make if I like, it's again close to diagonal. So the intersection of this is you can take a delta even in intersect with delta odd. So like intersection of this with this intersection of two Lagrangian subspaces, linear subspaces. And in our case, you replace one of these linear subspaces by non-linear, but very, very close to this linear. Right? So you kind of like, because you can spread all its, like the fact that it's very, very far from identity, you spread along many, many coordinates. So therefore, like on each coordinate, you just change a little bit. So in this space, this our Lagrangian is very much close to the diagonal, right? So the first, we need to therefore understand intersection of this as a intersection of this as some critical point of some function. And the question, we need to find this again, what is called Lagrangian polarization. You need to find some Lagrangian projection along some Lagrangian direction such that both of the subspaces, so we have a two Lagrangian, and we need to find some direction along which we can project without singularities the subspaces, linear, right? So we need to find this kind of like direction along which project. And what is this direction? This kind of, you do exactly the same what I did here. It's kind of what I call kind of alternating polarization. So you take like first coordinate in this space, x coordinate there, with y coordinate there, and then x coordinate there with y coordinate there, and complementary y coordinate here there. So you take this thing, and then the same argument as before shows that both of them parallel to this. And hence both of them are this Lagrangian, and both of them graph of derivative of some function. And because this is a linear Lagrangian, then linear Lagrangian are linear function are derivative of quadratic function. So therefore, there are two quadratic forms, like here I have the x1, y2, and here you similarly we have a x1, y2, and plus kind of like x1 prime, y2 prime, y2 prime, so kind of like exactly for the same as before. So you take this quadratic form, and so this quadratic form corresponds to kind of one of them, to even diagonal, and then you can kind of like you take another product in different order, and this will be in another one. And then what we need is the critical point of the difference. So you get difference of two quadratic forms. But what you'll see, okay, so I have to stop, but kind of like let me, or when should I stop? So do I have still kind of 5 more minutes? Okay. Okay. So you have a two quadratic form. Now, this quadratic form, these subspaces which I get, even diagonal and odd, they are not transverse. So if they were transverse, then difference of this quadratic form would be kind of maximal rank. But they are not transverse. Why? Because in all this space there is a common like diagonal which is just this equals this equals this equals this, right? So it's like full diagonal containing both of them. So we have this 8-dimensional space. In this 8-dimensional space you have a 2 4-dimensional Lagrangian, and this 2 4-dimensional Lagrangian intersect along the same 2-dimensional plane. And so this quadratic form is a kind of non-degenerate quadratic form of complementary to this. It's like equal to 0 on the subspace, and it's non-degenerate in transverse direction to the kernel. And now, but this is a Euclidean space. But what if I quotient by torus, then this full diagonal themselves becoming torus, right? Because I quotient each coordinate by this lattice, and this diagonal, of course, quotient the same way into the torus. So what I get instead of this, so you have two planes, and they kind of intersect along two-dimensional plane, but in the quotient, it's becoming torus. And the whole space, kind of on which my function is defined, is in fact becoming torus and plus this extra complementary R2. And my function, which kind of I get if before I perturb, function becoming like 0 on this one because it's just 0 section along this one, and plus some non-degenerate quadratic form along this R2.
Sir, can you explain this part again? How is it becoming torus?
We have our space. What is the whole thing? The whole thing is a product of R2, R2, R2. But in fact, this R2 was kind of where this R2 came. It was a covering space for our two-dimensional torus. Yes. So there was this lattice acting on each of them. Yes. And there is a diagonal, so there is a diagonal action of this one, and diagonal is invariant with respect to the section. Yes. So therefore, when I quotient every coordinate by the section, then diagonal will be quotient by the section. So diagonal becoming, so I'm saying let's quotient the whole space by diagonal action.
Okay. Yes.
Then you have a two Lagrangian plane, and their intersection becoming torus. Oh. But complementary direction I didn't quotient; it remained R2. Yes. Yes. So what I get function on torus cross R2, which kind of it does not depend on coordinates on T2 at all, but it's a quadratic form on this coordinate. But now I added some perturbation. And what it looks like, you get a function which is some kind of, so here's what you get. You get of a result of this construction, you get, oh sorry, very dangerous. So you take you get some function which is defined on torus cross R2. Well, in this case, torus cross R2, if I take just product of two copies, if I take a product of n copy, I get this R2n instead of R2, kind of as many of them. So you take this thing, and you have a quadratic function here. But then I perturb, and so I just add to this function, and what you can check that what you add some function. It may depend on all coordinates, but this function is kind of bounded in terms of all coordinates. This function is bounded in terms of all coordinates, and therefore, but with respect to this y1, y2 coordinates, this function is non-degenerate quadratic form. So this was a Q of this kind of y1, y2, this quadratic form. And so this function bounded, and for quadratic form, its derivative linearly is a non-degenerate quadratic. Derivative linearly grows. So derivative of this function at infinity goes to infinity. And when I add bound, and this is a bounded periodic function, so therefore this function, when I derivative never grows. And so if I just cut it off, I can, if I cut it out far away, so therefore you can, does not introduce any new critical point. And hence you get kind of like function which look on this one, which look like quadratic function plus something with compact support. This function, which depend only on torus coordinate, and in the x direction it's function which kind of like something and then just eventually 0. And so now this is kind of question how to, why such function must have a critical point. And this is a subject I will, tomorrow I will kind of like more systematically explain this in general context. This is a subject what is called stable Morse theory. So we have a, you can interested at function on given manifold or function on manifold say plus times Rn, and where you add some term, well, precisely this one, where you get function quadratic at infinity. And such function also must have critical point. But this is like pure topology which we can discuss. Okay, so that's proof Arnold conjecture for torus. And so you can kind of push it for some other manifold, but not, you cannot prove it this way for any manifold. So there was even, for instance, if you try to like for complex projective space to do this, so Giventhal proved this, but it's already becoming very, very elaborate.
And even in low dimensions, a genus higher than 1, is there some question?
No, for surfaces, for surfaces it's easy, yes. So for anything which is covered by Euclidean space, it's very easy. Yeah.
No, because there was this diagonal 4 things where isn't the torus coming into play there?
This argument kind of like would maybe not so easy to prove, but kind of but it can be done. No. Yeah, that's not immediate. So it's kind of like okay, like even you can say that it took. Okay, so as I said, I proved it for surfaces, but completely different kind of ideas. Then Conley-Zander proved it for tori, and kind of this is some kind of finite dimensional version of Conley-Zander proof. But then it took 3 more years before Floer kind of adjusted this proof to other surfaces. So it's not completely straightforward. You just talk about pseudogroup. So just consider, so you have like do the following things. So take any symplectic manifold, and then in symplectic manifold say take just some neighborhood and just consider not globally defined diffeomorphism, but just kind of embedding on just particular. So just embedding, symplectic embedding of one to another, and so the group operation defined not always but partially kind of as a, but this is called pseudogroup, this thing. And then you have the same statement. So the statement which you want to say that kind of if you have a approximation, if you like in this pseudogroup again there is no intermediate pseudogroup between volume preserving like embedding or symplectic embedding. And I think kind of like essentially everything which you talk kind of like can be without any issue adjust here, I think. And then that would kind of like remove this like issue. It's simply connected, not simply connected, because you only do it locally. So, of course, you know, in some sense, this theorem has only kind of historic interest, but I think it's still interesting. So, because, like, what a posteriori we know, right? That because okay, so now in this what we prove, that we prove what in the morning, that if you take that there are some volume preserving say diffeomorphism, say the one which is out fixed point, which cannot be approximated, that right? and so that's kind of, therefore for pseudo group is also not true, and therefore according to this theorem, it follows that that in fact if you have any kind of symplectic, say, embedding of, say, you take a ball and you consider it symplectic embedding to somewhere, any embedding kind of or whatever, which can be approximated, C0 approximated by symplectic, then it's itself symplectic, right? It follows. So yes, so it proves this kind of in this way, but kind of historically, this is not what happened, because historically, like the Gromov, for instance, gave this. Okay, there was some different proofs. So, like I think the published kind of proof first was Gromov, and kind of like with using holomorphic curve, and where was kind of directly proven this statement that everything which can be approximated without this thing. But what in fact happened that before all this, there was a proof of this Conley center theorem, which was proving this Arnold conjecture. But this Conley centers, they were not really symplectic geometers. They were kind of like coming from this different some analyst, I would say, and so they didn't know all this kind of like connections. For instance, this Gromov alternative was, though Gromov, like it's only appear in Gromov book, Gromov proved it long before, but kind of it's only appear in print. So they didn't know this. So they didn't know that the fact that they proved implies that via Gromov alternative that group of Symplectomorph, so it's a C0 close, so the limit, so they didn't know this, but it implied. So if they knew, they could deduce it because using this. So from kind of historical point of view, it would be useful, but it didn't happen this way. Yeah. So I also had some different proof of this, but again, it was a direct proof, not using this alternative.
One question.
Yeah?
This should be, this limit theorem should be more or less equivalent to saying that if you have a sequence of Lagrangians and C0 limits to some smooth submanifold, it's also Lagrangian.
I don't think this is true.
This is not true.
I think it's not true. I think that if you have a sequence of Lagrangian, okay, so that's a good question. I should know, but I think this is not true. If I remember correctly, that you can what?
Can we turn it into Legendrian?
What is Legendrian?
No, so the same question we might narrate it to Legendrian, sequence of Legendrians converging to Legendrian. We can say as well that's not true.
That's not true.
Yes.
Legendrian, we can take a non-Legendrian curve and
approximated by César Legendrian. Yeah, for Legendrian it's of course not true. Yeah, but I think for Lagrangian it's also not true. So I think so. It's a little bit too strong.
What does he mean by sequence of Lagrangian?
You have some manifolds.
You have a sequence of embedding, smooth embedding, and you know that it's smoothly, no, as a second, so, yeah, so it's you can approximate, and the limit, the convergence only C0, but limit known to be smooth. But the question is that limit itself, Lagrangian, Legendrian, but yeah, it's not true.
But given Legendrians, one can take the symplectization. I guess that's
Yeah, but then it will be not C0.
not C0.
That's not kind of
Yeah.
thing. So yeah, so I don't think you can from Legendrian deduce this the same for Lagrangian, but I think. ask first formal question, like about this. I kind of like I see that this audience kind of fluctuate. So there is some people, for instance, there was I think there was more people in your talk than in my lecture, and also than now. And so therefore, maybe there is some issue. For instance, there are some people who plan, for instance, to come only in the morning. I don't know if there such exist. And from this point of view, maybe it's not.
I mean, there are also
Classes going on.
there are
Classes going on. Ah, yes.
So some
Cannot come. So it may be not good really kind of to formally continue, because then if some people cannot come, then
yeah, that is
that's
because
good.
we have registered people.
Yes, we are.
only some number, and there are more.
More okay. Okay. So
Yeah, we can go up to 4 only.
Yeah, we can go up to 4 only. He said, because afterwards we have to do some.
yeah. But anyway. So I just don't want to kind of like say right now something which
But
kind
you
of
can-
which would be problem for people who come tomorrow to if I don't know.
Okay, but you can. We can have a. Anybody wants to ask?
Let's kind of better. I will not continue, but just we can a
Or you
little
can
bit
do some
expansion.
detail if you want to.
Yeah. So kind of like okay. So I think I didn't tell much at the morning. It was a kind of like what I started the first hour was kind of really some very general, and then what I was talking the second part. I hope it was clear, but I don't know if you have a kind of question. If you want me to explain better something, I would.
In the beginning, you mentioned this problem about Legendrian going from one point to another point with more slope at the beginning and in the front end. Then it is not. If you further assume it's graphical, then there is some obstruction. But if you don't assume anything, then there is no obstruction. It is the point that if you have to go from here to here, then there is a zigzag, but then you don't have a generating. Is that the point?
Yeah, because so I didn't really define yet any generating function. Yes, but kind of I will define it tomorrow. But indeed, the point is that so for so this is kind of Lagrangian manifold, and again. There is always in like symplectic geometry, there is always this kind of tension, what I call flexibility and rigidity. There is some results which kind of not possible. What, for instance, like we cannot eliminate fixed point of symplectomorphism, or so which would be possible if you could approximate by volume preserving, but. On the other hand, kind of many things are possible. There are a lot of construction, and so it always kind of the case when you slightly relax what you want to do, then suddenly it becomes possible. So and just kind of like general kind of like direction is that when you talk about Lagrangians, then when you have a Lagrangian embedded, then it usually become kind of more rigid object, and kind of like it's difficult. So for instance, you have a just a question. If you have a like R4, and you have some surface in R4, and you're asking when the surface can be deformed to be Lagrangian surface. So, and then it's kind of question about Lagrangian embedding versus Lagrangian immersion, where it kind of allows self-intersection as not a self-intersection. So, but in this case, of course, 2 to 4, then even if you allow immersion, let's talk, say, about orientable surfaces, right? So then, if you have a so suppose you have a surface embedded, and kind of like, then if it's Lagrangian, then multiplication by I give you isomorphism between normal bundle and tangent bundle. But but also this tangent bundle and normal bundle have a Euler class, right? So it's kind of like abstraction for construction vector field, right? So in fact, this condition that multiplication by I give you isomorphism does not mean that Euler class is the same. In fact, turns out to have to be opposite, because there is some sign issue, orientation issue involved. So there is a kind of necessary condition that it is, right? But then there is in dimension 4, there exists kind of Whitney theorem, which is of course simple theorem, which says, so we have a oriented surface, and what is a normal class? Normal class is the same as what is called self-intersection, right? Because if you take a surface and you're trying to construct normal vector field, and this normal vector field would kind of say have some 0, and you get, if you push it, you get some surface which have a kind of like intersection index, precisely this normal class. But on the other hand, this intersection index is a homology property, because, for instance, if I just pull the surfaces apart in the space, then it has to be the same, and therefore it has to be 0. So therefore, for any Lagrangian surface embedded in R4, normal class has to be 0. So therefore, tangent, like Euler characteristic, has to be 0. So it only can be torus, right? So the only torus can be embedded, but then you can. But this, and of course, it can be embedded, and no other surface cannot be. So, but then there was for many years that was an open problem about non-orientable surfaces. Suppose we have a non-orientable surface. When non-orientable surface admit Lagrangian embedding to R4, and then again by the same argument, Euler characteristic has to be 0, so therefore it only could be Klein-Bottle. So the question, can Klein-Bottle be embedded? And eventually it was proven that it cannot be embedded, but it kind of serious theorem. It's not a simple. Yeah. So actually, kind of like for Lagrangian, yes. But then you go to high dimension, then again there are kind of like a lot of constraint to topology of Lagrangian embeddings. And for instance, like the theorem is that if, say, manifold have a hyperbolic metric, hyperbolic, for instance, have a 3-dimensional hyperbolic manifold, then it cannot be admit Lagrangian embedding to Euclidean space. And so and that. So, but okay. So. What?
Why is this true?
So this, unfortunately, okay. So as my kind of like lectures about, I will be explaining whatever can be done with kind of finite dimensional thing. So that means that without using like analysis of, say, holomorphic curve or anything. But for this fact, I don't know how to prove it. Maybe it's possible, but I don't know. So I'll explain you briefly how you do that using holomorphic curve. So you do the following thing. So how does theory of holomorphic curve work? So do you anybody knows anything about this or okay? So so let's then I'll do 10 minutes introduction to theory of holomorphic curve. Okay, so here's the kind of like point. If you have a, so this is a kind of idea of Gromov and kind of the like beginning or whatever, Gromov with invariant, all the theory. So you started with symplectic manifold. And we know that like one of great example of symplectic manifold, the source one of like original sources of closed symplectic manifold is a Kähler manifold in complex geometry. So if you have a complex manifold which admit Kähler structure, then Kähler structure give you like imaginary part of Kähler structure is symplectic form, non-degenerate. And then this structure, this Kähler structure have kind of in addition has this property, okay, that what it means, that Kähler manifold. That means it admits some Hermitian metric. And so for any kind of two vectors, you have on every tangent space you have a Hermitian metric, and this Hermitian metric have a real part and has an imaginary part. I think you need by some reason write minus, but okay. You have an imaginary part, and this is a just usual Euclidean metric Riemannian, and this is a symplectic form. And moreover, they related by this, I think the g of xy is equal omega of x I y, I think, if I correct. Maybe I'm wrong in sign, but I hope correct. So you have this thing. And because this is a this metric is this metric is positive definite, so that in particular that implies so j of xx is equal to 0. So that means that omega of xix is greater than 0, right? So that means that if you take any like direction, any plane, which is a complex subspace, then symplectic form is positive on this, right? So this kind of Gromov call this condition taming condition. So if you suppose now you just abstractly you have some almost complex structure on the manifold, so that means you just introduce complex structure on every tangent space, and you have an almost complex structure, and separately you have a symplectic form. And then it has and the symplectic form is positive on all complex direction. So then we say that symplectic form taming this J. So why this is a kind of like, what is good about this taming is the following. So now forget for a second about anything symplectic. Suppose you're just interested about complex geometry and you would like to develop complex geometry but in not necessarily integrable setup. So we know that when you talk complex manifold, you can talk about holomorphic map of one manifold to another. But now you can, if in principle you have an almost symplectic manifold, say kind of M1 J1 and M2 J2, you can say, well, let's study holomorphic map of this to this, which means that differential of this map is complex linear at every point, right? So it's commute with J, this differential, right? So let's study this thing. So it's kind of great idea to study, but then you realize the following things. Let's see what kind of condition that this is holomorphic. Condition that this is holomorphic. So you have, for instance, this is say 2k dimensional, and this is a 2n dimensional. So then, how many equations we need to write to say the map is complex linear map, right? So you have like you take a Jacobi matrix, it's a 2k times 2n matrix. So you have a 4kn entries in this matrix. And if this matrix happens to be complex, then it has a kn complex entry, so it has a 2kn kind of real entries. So in order to say that real metric define complex linear map, you need to write 2kn condition. So you need to write 2kn condition with respect to with respect to 2n unknown function. You're looking for map, so you're writing 2n unknown function, 2kn things, and so unless k equal 1, this is an extremely overdetermined system, and for generic almost complex structure, it's kind of like easy to show that it never have even any local solution. So such map kind of do not exist if k is not 1. So even kind of like there is no reasonable theory in this case. So in complex case, is a kind of integral place. They happen to exist, but it's really very special situation because kind of a lot of cancellation in this kind of system happen because of integrability condition. Okay, but in general complex structure there is absolutely no hope for any theory. But for k equal 1, it's a determined system. So you have a 2n solution. So that means that when this is a Riemann surface, so that means, and for Riemann surfaces, almost complex structure always integrable. So therefore, it's just honest kind of Riemann surface with some. And for Riemann, so mapping of Riemann surface, this is a kind of reasonable thing. And indeed, when you study kind of locally, this is like elliptic system of equations. So it's a Fredholm problem. So for instance, for closed manifold, and you can it's some finite dimensional modular space of solution, which you can. So it's a perfect local theory of such map, absolutely irrelevant integrable case or not integrable case. But so you can kind of now that you're very happy. So let's start to consider what are like modular spaces of holomorphic curve in given almost complex manifold. But then in order to have a meaningful theory, you need to know something about topology of these modular spaces. And for instance, you would like to prove, say, suppose you have that you would like to prove that there is some invariant which independent when you deform almost complex structure, right? So you get some from some almost complex structure J0, and you deform it to J1, and then for instance, you fix M, say, sphere. So take CP1 with standard complex structure, and you consider this modular spaces of this curve. For this one, let's call it say M0, and you want to somehow compare this to M1. You want to say that they're related. And what you would like to say, well, you can do it for every t during this deformation. And of course, like you as usual, like for some t, kind of something could happen, but you hope that maybe there is some cobordism between these moduli spaces, and therefore they cobordin, and then maybe you can extract some homology type of invariant out of this. So that's idea that, but main thing which kind of needed that this moduli space is compact. Because it's not compact, kind of it go to infinity, and therefore absolutely you cannot like non-compact cobordism between two closed manifolds makes no sense. Kind of you can always do this, right? And so therefore again it becoming meaningless notion unless you have a compactness. And now kind of how can you ensure a compactness? And here comes this like Gromov compactness theorem, which says the following thing. So suppose you have a say sequence of say holomorphic curve, and how do you know that out of the sequence you can choose some converging subsequence, at least in some sense? Of course, you have to be kind of like be a little bit kind of inventive, looking what happened in integrable case. Even in integrable case, it's not kind of in order to talk about convergence. For instance, you take say CP1 cross CP1, and in CP1 cross CP1 you consider sequence of curves, say like something over this, right? So kind of graph of this thing. And then when epsilon goes to 0, it kind of like look at something bad happen. But what in reality happened, it converged to this to the split curve, what is called nodal curve. So you can also define this convergence, but you need to be a little bit more kind of accurate how you do it. But this is a well-known in kind of algebraic geometry how it's done, so you can mimic this definition. So and what Gromov proved, that you have this compactness, you have a convergence, provided that you know that with respect to some, you fix some background metric, and you measure just area, honest area of this curve, and as long as you know that during this sequence area is bounded, then you indeed have choose this converging subsequence. But the point is, what is the mechanism to control area? So you have a sequence of holomorphic curve, and absolutely there is a kind of like who can tell you that it's an area. Maybe they're becoming kind of wild and becoming extremely area go to infinity. But here comes symplectic form. So far all this have nothing to do with symplectic geometry. But now suppose complex structure which we consider, all this complex structure are what is tamed by some symplectic form. So you have some symplectic form, and this symplectic form is taming this one, so it's positive on complex direction. You only say for only consider say those symplectic structure. And by the way, notice a very simple kind of observation, that symplectic structures which are tamed by fixed symplectic form, all the symplectic structure form some contractible space, because they form, it's a section of some so-called Ziegler upper half space. So anyway, so this is a again well-defined fact that in algebraic topology that this space is contractible, and therefore there is a kind of homotopically canonical way to connect them, and therefore again for the purposes of defining invariance, that's kind of a good thing. So therefore you have this thing. So now how this helps? Because there exists what is called Wirtinger inequality, which says the following thing, that suppose you take a standard like Cn and take a standard metric and standard symplectic structure, kind of like as I define, and take any plane, and then let's compute, like take two vectors on this one, and for these vectors you can compute omega, symplectic form, and you compute their just area of this kind of parallelogram. And you always have one less or equal than another, and equality happens if and only if this direction itself is complex, right? So always area less than symplectic area always less or equal. No, what I'm saying? Yeah, symplectic area is less or equal than this one, and for holomorphic they are just equal. Now, this has happened for this is for the standard structure, and here you have a more than taming condition. You have also additional property here that this G invariant with respect to I. So we take so it's a more this thing. But even if you have a taming condition, then Wertzinger inequality still holds, but maybe with some constant. So it's not necessarily true that this is less, but less than some constant times this. So as a result, what we have? You have a holomorphic curve, and we know that up to some constant area, like universal constant depending only on this manifold, our any symplectic area for holomorphic curve is kind of the same as a just usual area. So if you know that integral of omega bounded, you know that area is also bounded. But integral omega is a closed form, so therefore integral of omega is a homology invariant. So therefore, if we consider our map and all of them say realize the same homology class, we know that area remain unchanged, and therefore you get bound for free. So that's a kind of reason why you have a Gromov-Witten invariant, why you can talk in the presence of symplectic form. So therefore this idea of Gromov, therefore the following: you take symplectic manifold, then you always have this contractible choice of the structure, and then you also need some kind of transversality, of course, some issue here, but modulo the transversality, you consider this modulo space of holomorphic curve, and then out of this you can try to extract some invariance, right? So, but then you can actually extract more. Namely, you have a so out of this invariance, for instance, you can prove some theorems. You can say, suppose you have a say you manifold. Suppose we are in 4-dimensional case, and say we are and let's take a product of spheres. Say CP1 cross CP1, and also here what is kind of sensitive, I need to say what are symplectic form I take. So I take some area form. So in fact on the sphere that's like area form, all of them are determined by total area. So it's only one invariant of symplectic form on surface is just area. And so you need to take kind of, suppose I take the same area, kind of like monotone case. So you have this area is the same as this area. And now you have a, and I'm now studying holomorphic curve in this case. So what is kind of like additional, so say I fix homology class, and I would like to analyze what is the modular space of holomorphic curve in, like, for instance, class 1, 0 in this thing. So then in this, if you take a holomorphic curve in the class 1, 0, then you have a kind of additional bonus property. Remember, all this Gromov compactness is up to this like nodal degeneration. It could be also nodal degeneration. But when you have a nodal degeneration, that means that your surface kind of becoming like nodal surface. And so therefore homology class, and every holomorphic curve, because integral of omega is not 0 and omega closed form is therefore non-trivial homology class, right? It kind of, and so therefore it's your class. This one split into kind of integer classes, such that for each of them integral of omega is positive, right? In this case, but just class 1 0 for this form cannot split this way. So if you slightly change, put this among f, so then you already have some possibility. So then things becoming much more subtle. But kind of as long as it's the same, then you don't have it, right? So therefore, this is a very special case, and therefore you get always this holomorphic curve, because for original, if you take a integral 1 and you know you can explicitly solve it, you know all this, your holomorphic curve, and therefore this kind of moduli space is exactly the same, kind of like up to in this case actually kind of literally on the spot the same, even nothing. There is something called even automatic transversality, which guarantees it's always kind of like there is no, even in the one parametric family, nothing happens. And therefore, it's kind of the same thing. And so that means for any almost complex structure, this like persists through every point, persists holomorphic sphere. And this holomorphic sphere, even in this case, even additional bonus, because there is this what is called adjunction formula, which tells that if you have a because if a holomorphic curve intersect, then index of intersection positive, again this is homology invariant, and therefore if they didn't intersect, they cannot intersect during any deformation. So you always have a fibration by this one, and this is a great thing. It's kind of like a lot of things can be proven. For instance, out of this thing you can deduce the following theorems, that any torus, if you take any Lagrangian torus in the say R4, then this Lagrangian torus through Lagrangian isotopy can be deformed to just standard split torus. So I'm set through Lagrangian isotopy because we can ask whether it's possible through Hamiltonian isotopy, and this turns out to be not true. There is some, but for Lagrangian isotopy, that means that you can. And what's the difference? The difference is that so if you have this torus has the following additional invariant. You can take a loop on the torus and take any disk spanning this and integrate form, and you get some number. It's called, so you get action of this class. So you get some relative two-dimensional, but in this case just one-dimensional cohomology class. For every loop you get some number. And this action class for split torus AB is just value A on one or pi r square on one and B on another. So you have a kind of different thing. And during the Hamiltonian isotopy, this number remain unchanged. And during Lagrangian isotopy, I can deform this torus, kind of varying this number. Okay, and for instance, so how this would you prove that all Lagrangian tori kind of are Lagrangian isotopy? So you take any Lagrangian torus and now start with a standard CP1 cross CP1, and it's foliated by this sphere. And then this torus in some kind of unknown way lies there. And now you consider the following deformation. So you take this neighborhood of this torus, and you do what in this gauge theory called stretching the neck. So you take a boundary of this tubular neighborhood, and you kind of start to insert in this boundary kind of some neck in such a way that what's happening is that if you okay, you need to describe it a little bit more detail, but you do some kind of degeneration of complex structure such that in the limit the manifold kind of split to the, so one manifold becoming just our manifold M minus L, kind of as if I just remove it, and another one became cotangent bundle of L. So kind of split this manifold. And what you can prove that our holomorphic curve survive all this cataclysm, and so therefore at the end you before had holomorphic curve through every point, and at the end you have a holomorphic curve through every point.
So this L should be thought of as something like an analog of a divisor, or?
No, but it's not. It's Lagrangian. It's not divisor, right? You can also play the same game with divisor. But you get some interesting result, and then this would be what is called relative Gromov-Witten theory, because then this holomorphic curve kind of which you get split again, you get some holomorphic curve in the line bundle over L. And
But, I mean, so the survival of the holomorphic curve is basically that the circle bounds what asymptotically small area.
yeah. So what happened? This holomorphic curve at the end, like from okay, well, this is of course going. I need more time for this, but kind of this holomorphic curve, which, for instance, in N minus L, in L, there exists. You say you also, in order to do this kind of degeneration, you need some kind of geometric data. For instance, you pick metric on L, and this metric determine. You take unit cotangent bundle, and then you get what called rep trajectory, which is just geodesics, lived geodesics. So therefore, and what happens that this holomorphic curve, they asymptotic to some geodesics on this one, and okay. Anyway, so this, yeah. But then coming to so and like to this original what I okay, we have to finish stop there. But I just want to say to this hyperbolic thing. So in the hyperbolic manifold, I know something beautiful about geodesics, right? You have like unique geodesic, and they are related, and so I have a lot of information about geodesic. And therefore, when I play this game, the splitting along this Lagrangian manifold, then I kind of can say exactly kind of what should happen, and then you get some contradiction. Okay, so maybe we have to go right now, or what? Or okay, okay.
Maybe you could give
Yes.
us a reference for this, for the hyperbolic case. Cannot we do that? Or is it?
Okay, so originally this is the theorem of Darboux, and there is a, I think this is a, I'm not sure where it's written in Darboux. Maybe in this paper about all these functors. This okay, but then this theory, the proof is completely different, and so I'm not sure. Is it? Maybe it's written. Is it written in our paper about the symplectic field theory? This introduction. Yeah, maybe it's written. I forgot if we wrote it or not. But if it didn't, then somebody else will maybe wrote. What?
What's the reference by Darboux?
I think this Darboux have this paper. There is some kind of functors and something in. There are two long papers, and I think it's one of them. Anyway, I can search if you're interested. I'll find. Okay, so see you tomorrow. No, this is not a talk, so it's not about.